All right, welcome back, everyone. It has been a busy week. This week we've had 4 midterms, 2 8A midterms, 2 8B midterms, so there's been quite a lot going on, but not to be left out and not to get behind, let's do some circuits today so that we can kind of wrap up the first part of Physics 8B, and then next week we're going to move on to magnetism and induction, and those two new topics kind of go together. So this is really kind of the trailing end of the first, maybe third, almost half of the course, and before we move to something new next week. So we're going to talk about circuits. I'll do a quick recap of the different components, some of which we already know, like capacitors we already know about, but resistors are new and batteries are new. And then we'll see how to, because circuits are very practical, we'll just see how to apply the loop law, the node law in a problem. We'll see how to solve for currents. We'll see how to combine resistors in series or in parallel. And more importantly, we'll talk about the RC circuit, which is kind of a very specific circuit. Like it's a little nugget in and of itself of knowledge. And sometimes it's covered a little quickly. And just want to do enough of a recap that we're clear on the difference between a charging RC circuits and a discharging RC circuits. So hopefully things went well this week with the midterm, and we can now move on to the rest and start preparing for midterm 2, which is going to come up really quick, as you already know, unless it's your first semester, which it probably isn't if you're taking Physics 8B. Once you hit midterm 1, just everything just speeds up incredibly, and like projects and papers are due, and other classes have exams and so forth. So it's going to get pretty busy. And so let's try to stay on top of stuff and cover this week. Again, I hope things went well. And if you are just stumbling upon this, you can find these live streams on slackademia.com. If you go to the study guides page, you can scroll to the bottom and enroll in the free course called Physics 8B Livestream. And if you want to contact me, you can contact me through the website. There's a contact form. Or through Facebook directly if you want to DM me if you have questions about, what now if the exam didn't go so well and you want to talk about options and strategies, feel free to reach out. So today we're going to talk about DC circuits. And really, if you think about what we've done so far, just zooming out, we've started with electric fields and then Gauss's law and then electric potential that introduced the idea of voltage. Then the application right off the bat was capacitors, and then we're continuing to move in that direction, and now we're going to talk about circuits where we're going to connect batteries with resistors and maybe also capacitors at the same time. And you can't make anything really wildly interesting with only those few components if you try to build a circuit, but they are fundamental components of a circuit. And if you take a circuits class, you can learn a lot more about the cool stuff you can do with circuits, but the idea is to just introduce you to this kind of part of physics, which we're not going to go too deep in, but we're going to cover a fair bit now. It'll come back a little bit later when we do induction, because we'll have a new component called an inductor, and we'll see how to deal with that. But by no means is this a circuit class, so it's still going to be pretty, surface level. We're not going to get into too much detail. But with that said, there is some meat on this bone, so let's kind of do a quick recap of DC circuits and how you deal with them. So let's introduce the different components that you might encounter when dealing with a DC circuit. And we'll just go through all of them real quick. Here I'm going to draw a battery. I'm actually going to, let me finish it, and so then I'll make a copy. So this is the positive terminal, which is longer. The negative terminal is shorter. This battery here, I'm going to make a copy of, and you'll see why. So I need to consider 2 scenarios. Then if I do this and I make the second terminal longer so that it actually, let me do this, so that it's equal to the length of the top one, then this is actually a capacitor. We know what capacitors are. We did a whole chapter on those. And then we have what are called resistors. And resistors are kind of new, and we're going to have to learn about them a little more and see how we deal with them on a circuit. Okay, so we know what an electric potential difference is. We said that's called a voltage typically. And we've seen the voltage across the capacitor plates before. So we're somewhat familiar with the idea that, okay, so if this is a capacitor C, this is a resistor R, and we'll get back to R in a second, then the voltage across the plates here is from minus to plus. We'll typically call it VC, maybe V cap, all right? But we say that it's a voltage, and that's the right word to use. In the case of the battery, you could say that the voltage across the battery plates, or terminals rather, is VB or whatever, that's fine. More likely than not, you would find that, yes, we draw the voltage arrow from minus to plus because that's the right way to draw it, but we denote this by epsilon, which we call the EMF. So this goes back, this is historical. I mean, EMF means electromotive force, and we actually thought that there was a force that we hadn't discovered and categorized yet that caused electrons, or charge in general, to flow through a circuit, and it turns out it's just the electric force, so JK, it's not a new force. But the electromotive force term kind of stuck, and that is what we call the voltage across a battery. So you can use voltage, everybody will understand, but you will probably see EMF or electromotive force. Usually we just say EMF. That's what that means. Okay. Let's be clear, this has nothing to do with epsilon naught. Okay. Epsilon naught is the permittivity of free space. It's the epsilon naught that's in Gauss's law. That's a physics constant. It has nothing to do with epsilon across the terminals of a battery. So let's just be clear about that. Okay, so what does a battery do? In Physics 8b, a battery supplies a constant voltage or constant EMF. Whatever happens, you can connect it to any circuit or whatever. In a given circuit, you put a battery, whatever the EMF the battery is, it remains that. Okay. Batteries, we never run a circuit long enough for the battery to die. Okay, so we never run the flashlight so long that the battery dies. We just have a battery, and we agree that it's an ideal battery and that the voltage across it is maintained constant. It's not exactly how a real battery works, but we don't have to worry about that. For now, we're just going to say, you know what? We're going to assume they're ideal. That's good enough to make the points that we're trying to make. Okay? And so then this ideal battery will supply a constant voltage to the circuit, and there are two options. It will either supply current, as in current will flow out of the battery, like this, call it capital I. Now, recall by convention, current is the flow of positive charge, even though, yes, in reality, it is electrons that are flowing through the circuit. We guessed wrong hundreds of years ago when we didn't have a good way to check, and it turns out we were wrong. But we decided to not rewrite everything to say, I is the flow of electrons instead of the flow of positive charge. So it's a convention. We agree that even though it's not representative of what happens in reality, if we just say that I is the flow of positive charge, we can solve all the circuits, and it works all the same, and we get all the same answers. So why bother rewriting everything and making charge negative? So current is the flow of positive charge. 95% of the time, if you have a battery in a circuit, it is there to supply current, all right? Which means that it supplies power to the circuit, okay? So this battery here is going to be supplying power. And in fact, the amount of power that it will supply is going to be epsilon times I. The voltage across the battery times the current coming out of it. All right. Let me just move this over a little bit. There we go. Okay. And so that's 95% of the time what a battery is doing in a circuit. And most of the time it's there to supply power to the circuit. That's how the circuit is being powered. However, in some circuits, you might have more than one battery. That's okay. And it could be that maybe one battery supplies power, but the other one is being charged. Just like you would charge your cell phone by plugging it into the outlet, batteries can be charged, and if they're being charged, then the current now flows into the battery.
Okay, so this is a battery, or being charged, or let's just say charging battery, that's just easier. And this charging battery is going to consume power P is equal to epsilon I. Okay, so now it doesn't supply power, which is energy per second, it consumes a certain amount of energy every second. All right, so that's for batteries. Then capacitors, capacitors at this point, we should be good to go. We have positive charge on the top plate, let's call it Q. And we know that Q is C VC. We know that C, at least for a parallel plate capacitor, is epsilon naught A over D, where A is the area of the plate, D is the spacing, so we have all that. And contrary to batteries, this capacitor stores energy, U sub C, which is 1/2 of C VC squared. Okay, so capacitors don't technically consume power or supply power. They just store energy for a while, and then they can give it all back if you want it all back. So that's the nice thing about capacitors. And so, but we've talked about capacitors. There was an entire chapter about that, so we're pretty familiar with all that. Resistors are new. Okay, so resistors are a two-terminal component. There's two terminals that are conductors. They're just not great conductors. So they will let current through, but what will happen is that they will have a voltage across them that opposes the incoming current. And basically they make it hard for current to flow through them, and the voltage that exists across them is proportional to how much current comes through. So now it doesn't matter for a resistor if the current comes from above or from below, as long as it goes through it. The only thing that you have to be careful about is that if you want to properly draw your voltage arrow, you have to draw it opposing the incoming current. Okay, so if the current comes up from the top like that, down from the top, VR has to point up. Now the reason is, and by the way, all of the current that enters the resistor leaves the resistor, just to be clear. You don't lose any charge in the resistor because you can't destroy charge, you can't create charge. So conservation of charge tells you that all of that current comes out the bottom of the resistor. However, because it's hard to go through that conducting material, it's a crystal lattice and the electrons are trying to get through, and it's pretty much like, you know, trying to jog through a crowded mall on Black Friday. It's like, it's hard to do. You're going to bump into people, and it's not designed for electrons to nicely flow through without any resistance. So because of it, the charge that enters here is going to have more energy, potential energy, than when it exits down here. And so the terminal of the resistor through which the current comes in has a higher potential than the terminal through which the current exits. That is why VR points against the incoming current for any resistor. Okay? And the voltage across the resistor is given by Ohm's law. And Ohm's law says that VR is equal to Ri. Okay, so it is proportional to the amount of current that goes through the resistor. All right, and a resistor, because what it does is that it allows charge to go through it, but with difficulty, only dissipates power. It cannot supply power to the circuit. It's just a piece of conductor and you're getting current to go through it, that's it. And so it can't supply power, it can only consume power, and it will consume the power P is equal to, now of course it's VR times I, because in all cases power is voltage across the component times the current through it. But because VR is also Ri, then it becomes Ri squared. And of course, if you want to say that, oh, well, I is VR over R, you could also write it as VR squared over R. Okay, both are valid. But be careful. For some reason, this one is easy to remember. Everybody tends to remember it. But you tend to forget that it's only valid for resistors. So you can't bust it out for a battery, because obviously a battery has no resistance, so there is no R defined for a battery. And therefore, this formula is only valid for the resistor. Okay, so those are the four, well, there's three components, but the four scenarios, because the battery could supply or consume power, that we're going to run into. We need to be able to draw current in a circuit. We need to be able to draw the voltage arrows. And then from there, we need to be able to apply what are called Kirchhoff's laws, which are the node law and the loop law. They're sometimes called the junction law and the loop law. And so we're going to go over that, but we could, do it theoretically, which really would be a repeat of lecture, or we could just kind of learn as we go by doing a couple problems, because I think it's easier to kind of grasp when you see it applied in practice. And like that, we can talk through setting up a circuit, which is an important part of solving them correctly. All right, so with this said, let's come down here. There will be a few more things that I'll say about resistors later, okay? Adding them in parallel in series, we'll do that in the last problem. And then the RC circuit in and of itself, we'll do a quick recap in the case of, in the last problem, because it's an RC circuit problem after all. So there are a few more things we need to kind of summarize and review, but for now, we've talked about batteries, we've talked about resistors. Let's see how we solve a circuit and how we would first set it up and then write Kirchhoff's laws. Okay, so for this circuit here, we want to find the current I through the resistor 3R that's diagonally set up like this in terms of V and R. Okay, so perhaps first things first. The only reason why we would draw a resistor slanted is to confuse you or to scare you. That's it. There's no real reason. You can make an argument that it's aesthetics, but I don't even buy that. It's really just to confuse you. So if you are confused by this, you can just say, look, what really matters is that it's connected to this wire here and this wire here. Let me straighten it out and maybe draw it vertically. Okay, so maybe we start by redrawing the circuit, okay, which is going to give us something like this. So it's going to be battery here with a voltage 2V. Then we're going to have a resistor here. And then if we look at what we had, that is going to be resistor R, by the way. And then we need 3R going down, 2R followed by V going down to the same wire. Okay, so the bottom wire is going to be here. All right, we need R going down. Well, 3R, but a resistor, okay, resistance is 3R. And then we need here a resistor 2R, followed by a battery with voltage V. It's going to connect down here. So this is V, and this is 2R. Okay, so if it makes more sense, you can draw this circuit like this. There is no difference. Okay? Then the question is, how do you set this thing up? Okay, so this is 2V, by the way. Should have written that. All right. So the truth is, unless you do circuits for a living, and you do a lot of them, you probably won't guess properly the direction of current. So it's a losing proposition to try to guess the direction of current right. And it doesn't matter because you're allowed to guess, and if it's wrong, turns out math is going to course correct you along the way. So the first thing you want to do in a circuit is draw the currents, okay, that flow through each branch. And a couple of rules around that. My default assumption is that batteries are here to supply current. So as long as I don't violate a law, like specifically the node law, I'm going to draw currents coming out of batteries. So for instance, I would draw this as a current I1. Okay, I1 is going to flow here through this resistor. And here I'm going to say that this battery supplies I2. That's going to flow like this. And they're going to meet here. This is called a node or a junction. And just like water flowing through pipes, they're going to merge and go down. Or at least that's how I'm going to draw it, because that's the logical way to do it. What you don't want to do, if you can avoid it, it's not the end of the world, but in theory, what you don't want to do is this. You wouldn't want to draw I3 coming like that, because then you do violate the node law in a sense. You say, well, there's three currents coming in, I1 plus I2 plus I3. That should equal the sum of the outgoing currents. And there's no outgoing current. So it still works. You can still do it with I1 plus I2 plus I3 is equal to 0. The equation will be valid for the node law. It's just kind of weird. Like, if you can choose to avoid this situation, I would avoid it. But worst case, even if you draw it like this, it's going to work. Okay? So, but what I would probably do is this. Say, okay, you want me to find the current I that flows through 3R. Okay, this is going to be the current I. And then the current here is going to split. Now, it's not obvious necessarily how it splits. You might want to call this I4 and I5 or whatever. But the truth of the matter is the following. If I have I1 coming out of the battery, I must have I1 coming back in through the other terminal. So the current here is actually going to split back up into I1 and I2, because on the right, same logic, I have I2 coming out of this battery. I need I2 coming back in. All right. So those are my currents. And I did not really violate the node law by drawing them that way. It kind of makes sense. I1 and I2 would merge into I and then split back up to each branch. Okay. So that's technically the node law. Okay. Now you have two nodes. You have a node here, that's A. This is a node here, B. This is not a node. This is just a wire that's bent at 90 degrees. That's it. Okay. To be a node, you'd have to have at least one other wire connect. Okay, so we only have two nodes, A and B. You can write the node law at either node. You will get the same thing, right? You will get I1 plus I2 is equal to I. Okay, that is the sum of the incoming currents equals the departing current. That's what I wrote here. But of course, if you go down here at node B, the sum of the incoming current, just I, is equal to the sum of the departing currents, I1 plus I2. So in both cases, you would get the same equation. I'm not saying that's always true. In general, you probably get different equations for different nodes in a circuit, but this one's simple enough that it just boils down to the same equation. So okay, I is I1 plus I2. You might even see, in some cases, people do this. They'll do what's called the node law on the fly. And be like, okay, well, I could bother to write this here, but why don't, instead of calling it I, I'm just going to call this current I1 plus I2, because that's what it is. Right? I don't even need to introduce I. I could just do this. I say this current downward through 3R is I1 plus I2. So some people do that, just, it's a little faster. But the point is, your goal is to first draw the currents, then you can write node law. You can write every node law. If you have 5 nodes, you can write 5 equations. And as long as they're different, right, then you have 5 independent equations, and that's good information. The next step is to draw the voltages in your circuit. Now, we made guesses here, right? I guessed that this comes out of 2V and that this comes out of V. I don't know if it's true. It doesn't matter. I'm going to stick with my guess. And now, consistent with my guess, I'm going to draw the voltage arrows across each component. Voltage arrows go from minus to plus. So for batteries, it's easy. It goes from the small terminal to the large terminal. Right? This is, well, I should draw it here next to V. Okay, so this is the voltage V, or the EMF V, if you want to call it that. And this is 2V. For resistors, the rule is that, of course, the voltage arrow will always point from minus to plus, but it's a little simpler for resistors to say that it points opposite the incoming current. Okay, so it points opposite the incoming current, like this, and like this. Okay, and just allow me in anticipation to do this. It makes no difference. It's just
to have enough room to write everything out. Okay. By the way, when you draw a circuit, however big you draw it, it will always be too small. That's just apparently a rule. So don't hesitate to make it big enough, because it's going to be a lot easier to be able to see everything clearly. Because you're going to have a lot of currents and a lot of voltages if your circuit is complicated. Okay, so I have my voltage arrows. I can do one better because I know Ohm's law. VR is R times I.
So this is R times I1. This is going to be 3R times big I. And this is going to be 2R times I2.
Fair? Okay. So I have my voltages. Now I'm going to write the loop law. Now, that suggests that there are loops, and indeed there we have loops. Careful that we have 3. There's usually more than you think. There's the left loop, the right loop, and the outer loop. Okay, so we have 3 loops. Usually, there are also more loops than you need. So, yes, if you have 3 loops, you could write the loop law 3 times, but you probably don't have to solve. Of course, that comes with experience, and you can figure out as you go, how many equations you need, and therefore how many loops laws you need to write. But I'm just going to, for the sake of practice, write all 3. Okay.
So we'll start with the left loop. And there's a couple of different ways that you can be taught to write the loop law, but
consistent with how we set up the circuit with first currents, where we guess, the direction, and then consistent with our guess for currents, we draw the voltage arrows. This is how I would do it. So the left loop is this loop, right? I'm going to go around the loop, and I'm going to add up all the voltages in the loop to equal 0. Okay. So the loop law says the net voltage around a loop, a closed loop, is 0. Now, you can go around the loop clockwise or counterclockwise. It doesn't matter, because you're going to get 0 in the end. And because the battery has a voltage 2V that's up like this, I'm probably going to decide to go around the loop clockwise. And you could indicate that if you want, like this. You might see like counterclockwise and clockwise arrows going around like that. That's all we're saying, is we're going around this loop clockwise. I think eventually you don't really need it. It's a bit overkill, and you can live without it. Like it helps at the beginning is all. But therefore, I am going to travel around my loop clockwise. As I travel around my loop clockwise, I will encounter these voltage arrows. I will encounter 3 of them in this loop. If the voltage arrow points in the direction that I'm traveling, that voltage is positive. If the voltage arrow points opposite the direction I'm traveling, it counts negative. So if I start like this, here I travel in the same direction as 2V, so 2V counts positive. Now I'm traveling to the right, but RI1 points to the left, so I subtract RI1. Now I'm traveling down, but 3RI points up, so I subtract 3RI, and then that's all going to add up to 0, because now as I go across this branch, there is no voltage to account for. Okay, well, it's not very complicated. Once you get used to it, it's pretty easy. But it's a nice way to not get your signs all messed up.
Okay, so let's practice again. Let's do the right loop. Okay, now let me get rid of this so we don't get confused. And if you were to give me the right loop, I would see V points up this way, so I would probably be tempted to go around the loop, but counterclockwise this time, just to go in the direction of V. It's kind of like that. It's my thing. But you don't have to do that. You can pick arbitrarily clockwise or counterclockwise. You can always pick clockwise if you prefer that. Nobody cares. We only care that you get your signs right. Okay, so same rule. As I travel around my loop, any voltage pointing in the same direction that I travel counts positive. So here I'm going to go up, V points up. Okay, so V is positive. All right. Then I'm going to travel here. There is no voltage to account for because there's no component, there's no resistor. So I don't worry about it. Here I go down, but 3Ri points up. So that's going to be, sorry, hold on. 1, 2, 3, let's backtrack this. My bad. I forgot 2R, didn't I? Let's do this again. I will travel here, upward. V points upward. So V counts positive, cool. But immediately after V, I have 2Ri2, points downward. So I got to subtract that guy. Okay, so minus 2Ri2. Here, no voltage to account for. Here I travel downward, but 3Ri points up, so I subtract minus 3Ri. And then there's going to be no voltage here, and so that's all going to add up to 0. All right. And then we will do the big loop or the outer loop, however you want to call it. And I'm going to, this time it doesn't really matter. Let's say we go clockwise, just to change it up one more time. So I'm going to go clockwise around the big loop, that's this guy. As I travel up here, 2V points up. Okay, so 2V is positive. Then as I travel across here, well, Ri points the other way. So Ri1 is going to be subtracted. As I travel downward, 2Ri2 points down, so that counts positive. 2Ri2, but V points up, so minus V. And then from here to here, there is no voltage to account for, therefore this all adds up to 0. All right. So it'll take a little bit of practice to get good at the loop law, but once you get it, it's actually not that bad at all. It's pretty easy to set up. Now, before we solve, because we still want to find this guy, that's the goal. Before we solve anything, let's remind ourselves that if we have, let's say, 3 unknowns, because while we don't know I1, we don't know I2, and we don't know I, we need 3 independent equations to solve. This is how math works. One equation will solve for one independent variable. Now, I have one equation here, so that's pretty good, which means I only need 2 more, so I can pick 2 out of the 3 loop laws. Now, again, we wrote all 3 just for practice, but also to point out the following. There will be more loop laws than you need, and very likely, at some point, you will find that loop laws are redundant. What do I mean? Imagine you consider the left loop law, this thing, and then you subtract this thing, right? Well, you're going to get this. You're going to get the big loop. So subtracting this minus this gives you this equation, which means that your third equation is not an independent equation. It's actually quite dependent. It is the combination of the left loop and the right loop. So you think you have 3 loop laws, but really in practice you only have 2, right? But that's okay. The node law is your third equation, and you can solve for 3 unknowns. Okay, so I'm just pointing that out because eventually, if you're not very careful in which equations you choose or how many you choose, you're going to get something like 1 equals 1 or 0 equals 0. And basically, it means you're going in circles, that you reuse an equation that you've already used before, even though maybe it might not look like it. So anyway, we get to this point. Okay, I want to solve for the currents, or basically I want to solve for everything, I1, I2, and then I'll add them together to get I. So I can pick 2 loop laws. Maybe I pick the left loop and the right loop. Why not? I mean, no particular reason, by the way. I'm just going to choose these 2. And I know that combined it's the same as this, so it doesn't really matter. And then I'll choose the node law for sure. Okay. So I have a problem when I want to solve this thing. I have these 2 equations here, but in these 2 equations I have all 3 unknowns. I have I1, I2, I3. Not cool. I would prefer to have 2 equations with 2 unknowns because I know how to deal with that. Okay, so this is why circuits
Circuits can get messy really quickly when it comes to solving. I'm not saying it's always true. Some circuits solve real nicely. It kind of depends what you're given. But in general, this is not a complicated circuit. Like, you will see more complicated than that. And it's already kind of complicated to solve. Okay, it's not that bad. Okay, because I can do this. I can say I is I1 plus I2. And if I substitute in there, then it will get my first two equations only in terms of I1 and I2. And that makes me happy because then I can solve two equations with two unknowns. All right, so then 2V minus R I1 minus 3R I is I1 plus I2 is equal to 0. And then the second equation is V minus 2R I2 minus 3R I1 plus I2. It's going to be 0. Okay. All right, so then this is, I can rewrite this 2V on the left, and then I'm going to throw all the negative terms on the right-hand side. So I'm going to get RI1 plus 3RI1. That's going to be 4RI1, and then plus 3RI2. All right, that's my first equation. And then I'm going to get down here, V is equal to, well, minus 3RI1 becomes 3RI1, and then plus 2R plus 3R is 5, so plus 5RI2. Okay, fair enough. And this is the same kind of equation as, it's like AX plus BY is equal to C1, and DX plus EY is equal to C2 or whatever. Two equations, two unknowns, right? So we know how to solve this thing. Our unknowns are I1 and I2. So what I can do is I can express I1 in terms of I2, substitute into the other equation, or perhaps something that works really nicely with circuits is to do the following, is to try to get these multiplied so that one of the two terms is the same in both. So for instance here, if I multiplied this by 3, I would get 12RI1, and then if I multiplied this by 4, I would also get 12RI1, and then I can subtract my equations. Okay, so let me do this. I'm going to multiply this whole equation by 3, this whole equation by 4, and I'm going to get the following. I'm going to get two new equations, but I didn't change the solution set, right? I'm allowed to do this. It does not change the solution set. So I get 6V is equal to 12R I1 plus 9R I2, and then 4V is equal to 12R I1 plus 20R I2. Okay, and if I call this equation 1 and equation 2, I can then do the following. I can combine these equations, I can add them together, I can subtract them, and I'll get a new equation, but I still have not changed the solution set. Mathematically, I'm allowed to do this. Okay, so let's say I take 1 and I subtract 2 from it. Okay, well then I'm going to get 6V minus 4V is going to be 2V. Then 12RI1 minus 12RI1 gets knocked out. That was the whole point. And then 9RI2 minus 20 is going to be minus 11RI2. Okay, so the nice part is I only have one unknown now. That's I2. It's easy to find. And then what I have to be careful is I had a system with two equations, two unknowns. In order to not change the solution set, I still have to have here two equations with two unknowns. So I only have one equation here. I need to choose one of the two, this one or this one. It doesn't matter which one. I just need to bring that one down so that I keep my system of two equations with two unknowns. Let's say I keep this one. I randomly picked one of the two. Okay, so then this is going to get me I2. Okay, now I2 is going to be minus 2V over 11.
R, because the R doesn't go away. There you go. So now I know I2. Okay, I know I2. Was there a minus? Well, the minus is telling me, you know, if you compute 2V over 11R, let's say you had values and you could compute this. Maybe you get, I don't know, you get 3 amps for whatever reason. Well, the 3 is correct. 3 amps is actually the amount of current. The minus here is telling me that my guess initially to draw I2 coming out of the battery on the right is incorrect. But I didn't know. And it was easier for me to just arbitrarily draw I1 and I2 than to try to convince myself that, oh no, I2 must flow back into this battery because this one's bigger and this is R, or whatever the reason is. Doesn't matter. Okay, so I made a guess. It's okay, I guessed wrong. I2 just flows back into the battery V. So, and I'll say that. I'll say I2 flows into battery V instead of out of it. Okay? I acknowledge that the minus means something, that the current goes the other way. Here's what I don't do. I don't go, oh shit, current's wrong, so oh, I got to change all this and I got to redraw it, so I erase it or I redraw the whole circuit, and now I2 is going this way, so cool, like everything's fine. I flip my voltage arrows when I need to, and I redraw the whole thing. Because guess what? Maybe I'm wrong about I1 too. Maybe not, but maybe I am. What am I going to do? Erase the whole thing again? Draw another circuit? I don't have time for this. Okay? So, what you do not do is redraw your circuit unless someone really coerces you to, right? Physically, with violence. So you don't redraw your circuit. You say, look, I get it. I2 goes the other way. I made a note of it. And what matters is whatever value comes out if I compute it. And in magnitude, it's 3 amps. It just goes the other way. And then you continue to solve your system. However, mathematically, right, this system doesn't know it's the system that represents an electric circuit. It's a math system of equations. It told you this is one of the solutions. You keep the solution as is with the negative because that is one of the solutions. Like math, again, doesn't know that you guessed the direction of I2. It doesn't give a shit. It said, okay, no, this is one of the solutions. So if you want to plug in I2, please plug in I2 with the negative sign because that will give you the other solution, I1, that will be correct given the equation that you set up earlier. So you do not redraw the circuit, and you certainly do not ignore the negative when it comes to plugging it back into your equations. Right? By the way, you don't rederive all your equations either, because no. Okay, so then we can say that was the first equation, gave me I2. The second equation is now 4V is equal to 12 R I1, which I still don't know, but plus 20 times, careful, minus 2V, well, sorry, it's 20R, my bad. All right, minus, so 20R times I2, which is minus 2V over 11R. Okay, so R is going to cancel out. And I am going to get, okay, now I only have one equation left, right? I have 4V is equal to 12R I1 minus 40V over 11. Okay. And so now I can solve this for I1. I can say that 4V plus 40V over 11 is equal to 12R I1. Okay, so this is 44 plus 40 is 84V over 11 is 12R I1. And so 84 divided by 12, that ought to divide. It's going to be 7, wow. Yeah, so I1 is going to be 7V divided by 11. R. There we go. By the way, I1 is positive. That's math telling me that the guess that I made initially to draw I1 coming out of 2V is actually correct. Now, of course, at this point, I already knew that because if I2 is going to go back into V, the other battery better supply power to the circuit because otherwise nothing's happening, right? I can't have two batteries that are magically charging and nothing supplying energy. That would not make sense. But the point is, you can guess I1 and I2 in terms of direction initially. You set everything up. If you're wrong, math will tell you, you acknowledge it, and you carry on with I2 being whatever solution that came out negative is. Whatever that solution is, you plug it in and you find I1. Okay? So I1 and I2 are not at all what I wanted. Not exactly anyway. And what I wanted is to solve for I. So I still have to answer the question. That would be I1 plus I2 is equal to 7V over 11R minus 2V over 11R. That's a terrible R down there, so let's fix that. Is equal to 5V over 11R. All right, that is the current going through the resistor 3R. All right. So hopefully the setup makes sense. Took us a while to get there, but of course it was worth explaining all the steps and emphasizing how you do things and how you get the currents, the voltage arrows, the node law, the loop law, how many you need, how you solve, and so on and so forth, because this is kind of the skill set that you need to solve circuits. Some problems will solve easier because the real problem is that we had all our variables mixed into two equations. So we didn't have a nice circuit where, one of the loop laws that I wrote only had one unknown, one current, and boom, I can just solve for it right there. That'll happen sometimes. It's always nice when it does. But if it doesn't, this is the way to go that's going to work every time. By the way, you do what you want, but I would strongly recommend solving in variable form and not plugging in values. First of all, you might not have values, so that takes care of that problem right there. But at least, I can check as I go. Like if I forget an R, which I almost did actually, I know that here's a current. Okay, Ohm's law, V is RI, so I is V over R. If this is a current here, if I see V, I better see R down here so that my units are not all jumbled up and wrong. So a pretty good idea to solve with variables for circuits, because if you start plugging in numerical values, it's just going to be a big mess. You don't think it's going to be, but trust me, ask me how I know, it will. So, okay, that's the first example. We have to start somewhere. It's not the easiest circuit ever, but it's a good example to learn how to set things up and understand how things work. Now this one is actually a bit more involved, let's call it that. And also it's going to allow us to find power. So that's a good little skill to practice, computing power consumed or supplied and deciding what happens. Okay. So here's a circuit that has 3 resistors and 3 batteries. Okay. And the batteries are here, VA, VB, VC. And we got R2, R3, R4. For whatever reason, there's no R1, but whatever, it doesn't matter. Now the first question is an interesting question. It says, is it possible for all 3 batteries to supply power to the circuit shown? Yes or no, or it depends on the voltage of the batteries. Okay. So not very common to have conceptual questions when it comes to circuits, but let's think through this. If you gave me this circuit, I would do the same thing that I did in the previous circuit. I would first draw currents, and in drawing currents, I would guess. I would say, you know what? In general, batteries are there to supply current to the circuit. So my default assumption, unless I do something completely wrong, is going to be to assume that I have a current IA coming out of battery A and flowing in like this. Same thing for battery C. This is going to be IC. All right, and then same thing for battery B. This is going to be IB. Okay, now the problem is that I get an issue at this node. I have 3 currents
converging at the node. So at the node, I have the sum of the incoming currents is IA plus IB plus IC. The sum of the outgoing currents is 0. But John, I thought you said that didn't matter, that you could write the node law that way, and so it was okay to have equal to 0 on the right-hand side. The equation's still valid. Yes, that's true. Mathematically, that's true. But that's not what the question is asking. The question is asking if it is possible, if you were to build this circuit, to have all 3 batteries supply power for the circuit shown. And the answer is no, because you'd have a problem here. If they all supply power, then at the node here, you have 3 currents coming in, right? You think of it as three hoses connected with a T if you want. The water comes in at the T, and there's no outgoing flow. Where'd it go? It vanished? Like water doesn't just vanish. For that matter, charge doesn't just vanish. You can't create or destroy charge. So it's not possible for all 3 batteries to supply power. No, for that reason. So it means that I got it wrong, right? At least one of these has to be flowing away from the node, but no more than 2, right? Because, okay, I mean, don't overdo it. Don't overcompensate. If you say, oh, IA, IC, and IB is like, okay, well, it's the same problem in the other direction. Magically, somehow at the node, I have 3 currents that get generated out of thin air and that flow away from the node. That doesn't work, okay? But at least one of them flowing away, yes, or even 2 if you want. But at this point, if I'm going to make a change, I'm just going to make one change. I'm going to change IB. Completely random. I have no good evidence to suggest that I should do that over picking IA or IC. I just picked IB. That's it. Okay, so now I have my currents. I can continue, by the way. I know that if IA leaves the battery, it has to come back in the other side. So this is actually going to be IA. That means that this is going to be IC. All right. And then I can draw my voltages. Voltage arrows go from minus to plus. So let's do the batteries first because those are easy. And then for resistors, well, voltage arrows point from minus to plus, but it's easier to say that they point opposite the incoming current. So here I'm going to get R2IA. That is going to be the voltage, points that way against the incoming current. This one is going to be pointing up. It's going to be R4IB. Maybe I'll move this here. Doesn't really matter, but just for clarity. And then here, I'm going to have voltage pointing opposite the incoming current. This is going to be R3IA. All right. Okay, so let's make a copy of this. And then let's find the power for R4 and state whether it is supplied or consumed. Okay, so I'm going to put that here, make it a little bigger. All right, maybe just get rid of the smiley face. We don't really need that. And then get rid of this little thing here by, okay, cool. All right, now is the power for R4 supplied or consumed? Well, at least I know that. It's always consumed because resistors always consume power. So that takes care of that. And then if I need to find the power consumed by R4, really I have to find IB, the current through R4. Because I'm going to argue that it's R4 squared. I'm sorry, R4 times IB squared is what I meant. Okay, so P4, the power consumed by R4, is going to be R4 times IB squared. It will be consumed. Okay, so what it means is I have to find IB. Probably means I just have to find all currents, IA, IC, and IB. Okay, because there's quite a few unknowns to deal with, and kind of like the other problem, I ended up having to solve all the currents to get the current I through the resistor 3R. So in general, in these types of circuits, the goal would be to solve for all the currents. And you can do it, right? You can just solve for all the currents and then figure out what you're being asked to solve for and determine that. So in this case, you'd solve for IA, IB, IC, and then you go calculate that and you said, okay, done deal. All right, and that's fine. And you would do what we did before, right? You would write the node law.
Okay, so maybe let's write the node law. All right. We have two nodes here. We have node A and node B. It doesn't matter which one you pick, you'll get the same thing. It's going to say IA plus IC is equal to IB.
And then we have 3 loops, right? Just like before. Left loop, right loop, big loop. You can write all 3, or you can just pick 2 out of 3, and you can go and solve. Okay, so you could do that. There's nothing wrong with it. I don't want to exactly do the same solving as the previous problem because I want to help you think through this and try to see, well, is there a faster way to get IB? Because as fun as loop laws are, if I don't have to solve for 3 unknowns and I can just get IB directly, that would be nice. So let's investigate. If I look at the loops that contain IB, because if I want to solve for IB, I have to look at the loops that contain it. Start with the left loop. If I were to write the left loop, VA would be part of it, but I know VA. R2IA would be part of it, and I don't know IA, so I'm pretty sad about that. This would be part of it. Well, thank God, because that's the point. I'm going to solve for IB. And then here again, IA. But I don't know IA. So it's not enough to just write that loop law to get IB. Okay. But what if I consider this loop? If I go around this loop, I'm going to get VC, but I know what that is. I'm going to get R4IB. Cool, because I want to solve for IB anyway. And then I'm going to get VB. Well, I know what that is. So in fact, in this problem, which I couldn't do in the previous one, in this problem I have a circuit that is in fact simple enough that just writing the right loop law will give me my answer directly. So I'm going to do that, right? And maybe, just maybe, I will still have to solve for all the other currents later to get the answers to the other questions. But for now, you know what? Yeah, I'm just going to write the loop law in the right loop, and I'm going to get IB, and then I'm going to compute P4. Okay, so the right loop is this loop here. If you were to give me this loop, I don't know what I would choose. Maybe I'd just go, I don't know, let's go counterclockwise. It doesn't matter. There's 2 batteries in it, so I'll go along VC and then we'll write the rest. Okay, so as I travel upward, VC points up, so VC counts positive. As I travel across, there's no voltage here. As I travel down, I go against R4IB, so minus R4IB. And then I go against VB, so minus VB. And that's going to be equal to 0. Okay, well, so that means that if I solve that, I can just directly get IB is going to be VC minus VB divided by R4. Okay, I can compute that. I know VC, I know VB, and I know R4. Okay, so VC is 12, minus VB is 4, divided by R4 is 4. So that's 8 over 4. That's 2 amps. Okay, by the way, it's positive. So I switched IB from flowing upward to flowing downward, complete guess. I got lucky. That is actually the direction of IB. Okay, so that's going to be 2 amps, and I know that. It's not what I want to solve for, but it's what I needed to get P4, and to say that P4 is equal to R4 IB squared. R4 is 4 times 2 squared. That's going to be 4 times 4 is 16, and power is expressed in watts, which is the same thing as joules per second. So in other words, every second, this resistor dissipates 16 joules of energy from this circuit. All right. So that's for question 2. Okay, and this is, by the way, just to be clear, this is consumed. All right. Then find the power for VC, state whether it is supplied or consumed.
Okay, now the power for VC, by definition, is going to be VC times IC, which means I have to solve for the current IC. All right. Now the thing is, the current IC, if I look at it, never flows through a resistor, meaning that it never shows up in a voltage, right? IA flows through this guy, so I get R2IA as a voltage. So that's going to show up in the loop law. Same thing, R4IB shows up in the loop law. But IC doesn't flow through a resistor, so I cannot get it in my loop law. So I'm going to have to solve for IA, and then I'm going to have to use the node law to get IC. Okay? So let's solve for IA. To do that, probably going to use the left loop, right? And let me just let's see if I can make a copy of the whole thing without messing this up. Oh, there we go. Okay. All right, so then I'm going to solve for IA first, and then I'm going to get IC. Okay, so the left loop. You go around clockwise or counterclockwise, it doesn't matter. Let's do clockwise this time just to change things up. As I travel around clockwise, I move up this branch. VA is in the same direction that I'm going. VA counts positive. Then I go across like this. That's opposite R2IA, so I subtract R2IA. I go down. That is against R4IB and VB, so minus R4IB minus VB. And then here I go this way. That's against R3IA, so minus R3IA. Is equal to 0. Okay, so that's fine. I chose, I'm being a dum-dum, because if I put 2 seconds of effort into thinking about this, I should have chosen this loop. It would have been a lot easier. I would not have had to deal with this and this, but it's okay. Doesn't really matter. Doesn't matter which one you'd write. Let's just stick with this one, okay? So then we get VA minus VB minus R4IB is equal to R2 plus R3 IA. All right, so IA is going to be equal to VA minus VB minus R4 IB divided by R2 plus R3. Okay, well, I can compute that. Maybe I just, maybe I just bring this down here so that I have enough room to do it right here. Okay, so what's that going to be? All right, well, VA is equal to what? VA is 7, minus VB is 4, minus R3 is 3, minus R4, my bad, which is 4, times the current, which is 2, that's IB I just found, and that's going to be divided by R2, which is 2, plus R3, which is 3. Okay, so that's 7 minus 12 over 5, which is minus 5 over 5, which is minus 1 amp. Okay, so 1 amp is correct. The minus tells me that IA actually flows the other way. Turns out IA also flows away from the node and back into VA. Right, so I can make a note here to acknowledge IA flows into the battery VA. It's okay, I guessed wrong. Again, math will course correct and tell me that I guessed wrong. But in the context of the equations I've set up and the circuit that I've drawn, IA is minus 1 amp is actually one of the solutions of the solution set. So I'm going to keep that. And so when I'm solving for IC, which is what I want, and I'm going to solve for IC with the node law, I'm going to say IC is, now that would be IB minus IA, that is going to be, well, IB is 2, minus, careful, minus 1. So then I get 3 amps. Okay, so IC is positive, which means that my guess to draw it flowing out of VC is correct. Therefore, I know VC supplies power, right? Because the current comes out of the battery. Okay, so IC flows out of VC, which means VC supplies power. How much power does it supply? Well, it supplies a power PC, which is VC times IC. VC times IC, what is that? That is 12 times 3, which is 36 watts, and that is supplied. In fact, VC is the only battery that supplies power to the circuit, right? It has a voltage large enough that in fact it charges VB and VA, and that's just how the numbers turn out here, right? So, same method as before. Like I mentioned earlier, maybe sometimes you get lucky. One of the loop laws only has one unknown, and you can solve for that. It's a little easier than solving a system, right? Because notice now, because I had IB, I actually didn't have to solve a system for IA. I could just write the loop law in here, and I can get IA directly. It's quite nice. And it's not uncommon to have that in circuits. Just you should also know how to solve a system with 2 equations and 2 unknowns if you ever have to. Okay, so that's that circuit. Then let's come down here and have a look at this thing. All right, so this is an RC circuit, which means it's a combination of at least a resistor and a capacitor. Sometimes a resistor and a capacitor and a battery. Sometimes it's actually multiple resistors and multiple capacitors, but I can combine resistors into one equivalent resistor, capacitors into one equivalent capacitor, so I can bring myself back to the battery plus resistor plus capacitor scenario, which isn't bad. Okay. Now an RC circuit is a really interesting circuit. It's kind of the first a bit more complicated circuit that we can encounter. I'm going to do a quick recap here. I'm not going to go in all the details. That's all covered in the lecture notes online if you need. And the RC circuit it depends which one. So that's the thing. It depends whether you're trying to charge the capacitor or discharge the capacitor. So I'm going to draw 2 different RC circuits. I'm going to start with the one with the battery because it actually is the most common one. Now sometimes you'll find that we put a switch and then you can put the resistor first followed by the capacitor, or the capacitor followed by the resistor. It doesn't matter, right? As long as they're in series, that's all that matters for this. Okay. So the battery is going to have an EMF, or voltage epsilon, typically. This will be C, this will be R. And as we close the switch at t equals 0, what happens is that current will start flowing out of the battery through the circuit. And that current, now usually current when I connect, say, like in the previous problems, when I connect a battery to resistors, once I connect them, whatever current comes out immediately. I don't have to wait for it to build up or anything. But here, if you combine a resistor and a capacitor, it's kind of weird. The current is going to start out very strong. It's going to come out of the battery very strong, and then it's going to die. Because as the current comes out like this, it's going to bring positive charge to this top plate. And at some point, there's so much repulsion on this plate that you can't, it gets harder and harder to bring charge, but at some point you cannot bring any more charge. It's like stuffing people into the metro. Like at some point you just can't put another person. And so
the current starts out strong because there's plenty of room on the capacitor plates, and so the charge is like, hooray, let's go. And then it gets super crowded, and eventually the current dies.
So that means that the current is going to be a function of time.
And you could call it little I or big I. There's kind of a convention, which is that if you write little I, you mean that it's a quantity that changes with time. Whereas if you write capital I, it's the current, the final current established. It's a constant value. So you probably will find little I of t written like that. Doesn't matter too much. And then, of course, just to be clear, this top plate is going to accumulate an amount of charge Q, which of course will be a function of time. Okay. And the whole point is to track how does Q change with time. And so if you draw the voltage arrows in this circuit, and if you say that this is R I of t, and you say this is VC, which by the way is Q of t over C, because Q is CV for a capacitor, then if you write the loop law, as long as you remember that the definition of current is dq dt, then you're going to get the following. You're going to get dq dt plus q over rc is equal to epsilon over r. And this is a differential equation, right? It is a relationship between a function q and one of its derivatives. So at some point in your life, maybe you knew how to solve differential equations. We do not expect you to know how to solve them in Physics 8b. You are expected, however, to know what the solution looks like. So if I have a charging capacitor, the solution is going to look like this. It's going to be Q of t is equal to C epsilon 1 minus E to the minus t over RC. All right. And this term here is sometimes called Q max because it is the max amount of charge you're going to be able to put on the capacitor plates. And it looks something like this. If you were to plot it, this is T, this is Q, and Q max is going to be an asymptote. Right? You cannot exceed Q max. Right? That is the most amount of charge you can store on those plates. And then the growth is actually exponential. So it starts out pretty solid and quick, and then it dies off with this as an asymptote, something like that. All right. And then the final thing to know about this type of circuit is that tau is called the time constant, and it is RC. Okay, now it gives you an idea of how long the transient state lasts, like the state where things change quite a bit. Okay, we're not going to get into nitpicky definitions of what the transient state is and when it ends and whatnot, but tau is a measure of how long it takes, in a sense, to charge a capacitor. Now careful, I did not say that tau, if tau is 7 seconds, that after 7 seconds your capacitor is full. I didn't say that. I said if tau is 7 seconds, that is roughly the order of magnitude it takes to get 2/3 of the way to full charge. So 7 seconds, the rule of thumb is if you multiply, 5 tau or 6 tau, roughly. So like call it 6 times 7, that's 42 seconds. Okay, 42 seconds after you've started, you pretty much have a capacitor that's full of charge. Okay, and this is ballparking it, right? But the idea is that tau gives you an idea of how long it's going to take. 7 seconds, even if you multiply by 6 and you get 42, okay, you're counting in tens of seconds. Versus, is it hundreds of seconds? Is it days? Like, I want an order of magnitude. So it's an order of magnitude of how long it takes to charge your capacitor. Now, by the way, just to point it out, here you have dq over dt, which is charge over time, which means that this also has to be charge over time. That's why this is your time constant RC of your circuit, right? So that is if you have what we'll call, or at least what I will call, a charging RC circuit. So let me move it here so that we can, there we go, we can write charging
RC circuit. Okay. Now, charging RC circuit is going to require a battery because something has to provide the charge that you're going to dump on the capacitor plates. Typically, the capacitor starts out being empty, and then you connect it to the battery, and charge accumulates until it reaches Q max. Okay. Sometimes you will have what's called a discharging RC circuit. All right. Now, the discharging RC circuit tries to do the opposite. It tries to take charge that is already on the capacitor and discharge it through the resistor, which means that it does away with the battery. And so you're going to have a capacitor here. The only thing is that this capacitor, instead of starting out empty, is going to have to start out with a certain amount of charge on it. So one way or another, you're going to have to put charge on this capacitor, and then you're going to have to connect it to this resistor. Okay, so this is going to be R, this is going to be C, and let's say that this is the positive plate. The positive plate will carry an amount of charge Q0. Okay. Now there's clever ways to do that with three-way switches or whatever the case may be. Sometimes you see that in lab. But the point is, one way or another, you have to have a certain amount of charge on your capacitor at first, and then you connect it to the battery, maybe with a switch. This will be VC, this will be VR. And what you're going to get is a similar type of behavior where if you write the loop law, you're going to get this, but it turns out that because there's no battery, the right-hand side is going to be 0. And by the way, in this case, I would be minus dq dt, okay, because actually dq dt is going to be negative, right, because capacitor loses charge, so Q decreases. And so you put a minus so that the current I represents a positive quantity. And then that changes your solution. Your solution is going to be Q of t. It's going to be equal to Q0 e to the minus t over RC. Okay, and so in terms of behavior, it's going to be an exponential drop in charge. Q versus time. If you start at Q0, it's going to drop exponentially, and the asymptote is Q equals 0. And it's still true, though, that tau is equal to RC. That doesn't change. That's the time constant of your circuit. And again, it's an order of magnitude of how long the transient state lasts. In other words, here, in this case, it is an order of magnitude of how long it takes to empty all the charge off the capacitor. Because at some point, there will be no charge left on the capacitor. All right, so that's a brief recap, but I did want to do it mostly to emphasize the fact that you have two options when it comes to the RC circuit. It could be charging, which is probably like 90% of the problems, or discharging, 10%, but discharging still happens. You have to be able to establish this differential equation. That is fair game. You don't have to know how to solve it, but you have to know that this is the solution. Same thing here, you have to establish this and know that the solution is this. Most of the time, the functions Q of t are provided on the equation sheet, which means you just have to pick the right one, which means, of course, you have to know what you're dealing with and what the right one looks like in each case. All right, so with all of that said, let's, well, actually, no, sorry, one last thing before we jump into that circuit below. Okay, one last thing is resistors in parallel and in series. Okay, so let me just draw a resistor here. This is the same logic as with capacitors. It's just that resistors don't behave the same way. So I'm going to put two resistors in parallel, and I'm going to write our equivalent. Then I'm going to put two resistors in series, and I'm going to write our equivalent. And that's just a quick recap. Okay, so this is R1, R2. I'm going to connect them in parallel like this so that they have the same voltage. Two resistors in parallel are equivalent to the single resistor are equivalent, where R equivalent, well, actually, where the way to compute it is this, is 1 over R equivalent is 1 over R1 plus 1 over R2. Okay? That's just resistors in parallel, which is the opposite of capacitors in parallel, right? C1 and C2 in parallel, C equivalent is the sum, C1 plus C2. Here they add as inverses. And of course, if they're in series like this, then we're going to get R1, R2, one after the other is equivalent to a single equivalent resistor with equivalent resistance that is the sum of the two. I mean, it makes sense. If you're trying to flow through R1 and R2 in your current, here you're going to have to jog through the crowded mall once, and then, oh no, another mall, jog through that mall too, right? So it's harder to go through two resistors in series if you're current than if you're, than if you're just going through one of them because they're in parallel. So it makes sense that our equivalent should be the sum of R1 and R2. Okay. So the formulas work exactly opposite those of capacitors. Just, keep your ducks in a row, know which one is which. Now, I say that, and I go over that now for the following reason. In this problem, we have an RC circuit. The problem with this RC circuit is that it looks nothing like the RC circuits I drew above. If you zoom out and you go have a look, you're like, well, there's only one resistor and one capacitor. Now I show up for the exam and I get this thrown at me. What do I do with it? Okay, well, it's okay. I just take this and I transform it to what's called an equivalent circuit. And in fairness, the first question asks you to do that. It says, draw a simplified version of that electrical circuit using only one resistor of equivalent resistance R equivalent and one capacitor of equivalent capacitance C equivalent. Okay, and express R equivalent and C equivalent as a function of R and C. Okay, so let me take this and bring it down here. Let's just talk about this real quick. Okay, so the equivalent circuit is going to be this. It's going to be the same battery connected to one single resistor with resistance R equivalent. Doesn't matter if it comes before the capacitor or after. Right, so that you can put the capacitor first if you want, nobody cares. As long as they're in series, that's all that people care. And then here's going to be C equivalent. And this is going to be epsilon plus minus. And I'll draw the currents and the voltages after. For now, I only need this. Okay. Now, you might say, well, how do I deal with resistors in series and capacitors in series or parallel or whatever if I have a mix of them? Well, you separate them out. Okay, so let's forget about capacitors for a second. Just imagine they're not there. R1, well, are the two resistors, let's just say it that way, in series or in parallel? Okay, now, careful. In series is always easy to spot, right? They're one after the other. Any current that flows through this one, any current that flows through this one must then flow through the second, which is the case here. They're in series. You might say, oh, no, but they look parallels. No, I got you. I get it. They look parallel. Yes, they're not, right? In parallel means you're connected across two wires the same way, right? A blue wire and a red wire. Both resistors, top connected to red, bottom connected to blue, okay? Well, here, let's draw these, okay? The red wire maybe is this one, okay? And then the blue wire is going to be this one. Okay, well, if you think about it, these two resistors are not connected the same way across these two wires. Right? The top resistor has the left terminal connected to the red wire, but then the other terminal is connected to the other terminal of the bottom resistor, and this one has a left terminal connected to the blue wire. So these are not in parallel. Just because they're parallel to each other geometrically does not qualify them to be in parallel. Right? To be in parallel, they would have to be connected the same way across these two wires, just like these two are. Okay, and if you're not convinced, you can stare at this for a minute, but you should at least convince yourself that they have to be in series, right? If, let's imagine so you're a charge, let's say you're positive charge, because current is positive charge.
and you want to go through a resistor, okay? And okay, you go through the resistor, and when you go through this resistor, they give you a little receipt. Say, hey, you went through, here's your receipt. Okay, you come around here and you enter this guy, and then you have to give a receipt to go into this guy. Okay, well, you got a receipt here, you can give the receipt here, right? In other words, every single charge that went through this guy here ends up having to go through this guy here to make it around the circuit. So that means that you're in series, right? The one after the other, there's no choice other than that. Okay, so these two resistors are in series. So R is in series with R, and R equivalent is going to be 2R. Okay. Then I forget about the resistors. I only look at capacitors. Hopefully we're convinced that these capacitors are in parallel, not because they are geometrically parallel, but because if you look at this wire here and then the wire on the other side, both capacitors are connected the same way across these two wires. The top connected to the red wire, the bottom is connected to the blue wire. So C is in parallel with C. Okay, so then C equivalent is equal to 2C, because capacitors in parallel just add. Fair? All right. Okay, so then what is the, that's it. What is the equivalent circuit? Well, it's C, R equivalent is 2R, and C equivalent is 2C. Okay. All right, so then let me just check something real quick here. All right, yeah. Sorry about that. Okay. Okay, so we have our equivalent circuit. Okay. Then we're asked to, well, we're told before the battery is connected to the circuit, the capacitor is uncharged. And we will connect it to the circuit that has a battery to charge it. So we are going to have a charging RC circuit. Establish the differential equation satisfied by the charge Q accumulating on the equivalent capacitor plates using R equivalent and C equivalent. You do not need to solve. We will provide you with the solution. Okay? Fair enough. So, epsilon is the voltage across the battery, and the current is going to flow like this. It's going to accumulate charge on the top plate. The voltage across the resistor is going to be R equivalent times I, and this is going to be VC is just Q over C equivalent. Okay, because Q is CV for a capacitor. Now, two things to remember. If you want to establish the differential equation in Q, which we mentioned above, I didn't derive it above, but we're going to do it now, you have to remember two things. For a charging capacitor, I is going to be dq dt. Now, I guess they call it big Q here, so I'll use big Q, which means I have to change this here. Change this to big Q. There we go. I is dq dt, and then the way I find the differential equation is I write the loop law. Okay, so I'm going to go around my loop. I only have one loop, so that's pretty easy. Let's say I go around clockwise, like this. All right, and as I go around my loop, I travel in the same direction as epsilon, so epsilon counts positive. Then I travel from here to here against R equivalent I, and from here to here against Q over C equivalent. So I'm going to get minus R equivalent I minus Q over C equivalent. And that's all going to be 0. Okay, so what is this? This is going to be epsilon is equal to R equivalent times I, which is dq dt, plus Q over C equivalent, which I can rewrite, and I'm going to try to match the form I have up there. I'm going to rewrite dq over dt plus Q over R equivalent C equivalent is equal to epsilon
over R equivalent. That is my differential equation, right? It is a relationship between a function q and its derivative, or one of its derivative, in this case the first derivative, dq dt. And we were asked to do it using R equivalent and C equivalent, okay? So let's just real quick go back up here and compare to this. I know I have a charging RC circuit, and I know that if this is my equation, this is my solution. Okay, so allow me to do this. Let's bring this down here. Because my point is, again, they're probably going to give you the solution anyway, right? So I'm going to gray this out because I don't want to be, it's not what I'm trying to emphasize. I'm just trying to refer to it. And I'm going to change it just a smidge so that the Q's are all big Q's. So I can easily do the comparison between the left-hand side and the right-hand side. Okay, now the only difference is that on the left I have R and C, on the right I have R equivalent and C equivalent. Is that correct? So it means that Q of t is going to be C equivalent times epsilon times 1 minus E to the minus t over R equivalent C equivalent. Okay, so I don't have to reinvent anything. I can just use what I found for R equivalent and C equivalent, and that will give me Q of t. Okay, so this is going to be 2C epsilon 1 minus exponential of minus t divided by 2r times 2c is 4rc. All right, that's going to be Q of t in this case, which nobody asked me to do that. I'm just showing you how you would go from your differential equation to the solution if you were given this. And of course, if you just had R and C, then yeah, that's just the answer. Whatever they gave you is, you're done. You don't have to worry about R equivalent and C equivalent. But that's how you would do it in this case. Okay, so determine the current I flowing through the equivalent circuit immediately after the battery is connected to the circuit. Draw a qualitative plot of the current as a function of time. Okay, let's get the current as a function of time. So we said Q of t is equal to 2c epsilon 1 minus e to the minus t over 4rc. And we said also that I of t is equal to dq dt. So really all I have to do is hit this thing with the derivative. I just have to remember the chain rule, which is e to the u prime is u prime e to the u. And in particular here, if u is minus t over 4rc, then actually u prime is minus 1 over 4rc, because my variable is t with respect to which I'm differentiating. All right, that's what dt tells me here. Okay, so then the current is going to be given by, derivatives don't care about constants, so 2ce just stays out front. And then in here I take the derivative of this. Okay, well 1's a constant, so it differentiates to 0. Minus u prime is minus 1 over 4rc. E to the u, which is minus t, over 4rc. All right, so that's I of t. And if I want the current at t equals 0, so right after the switch is closed, sorry, I'm jumping the gun here. Let me simplify this. I don't know what I'm doing. So, okay, so 2 over 4 is 1 over 2. Minus and minus becomes plus, and the c's go away. So this is epsilon over 2r e to the minus t over 4rc. Okay, so that's going to be the current as a function of time. And if I want the current when t is equal to 0, it's going to be epsilon over 2r, e to the 0, which is 1, so it's going to be epsilon over 2r. And by the way, if I were to graph the current, it is a decreasing exponential. So if this is I and this is t, the current would start at a value epsilon over 2r, and then exponentially decay, with 0 being an asymptote. Let's try to show that a little better. Something like that. There we go. Okay. And then finally, what is the maximum electric potential energy that can be stored by the equivalent capacitor in terms of R equivalent and C equivalent? Okay, well remember that we wrote initially, when we did the quick overview, that this amount here is going to be Q max. It's going to be the max charge that can be stored on the capacitor. So the maximum potential energy that I can dump onto the capacitor is going to be given by U C max is equal to Q max squared over 2, well, the C is C equivalent really. So this is going to be C equivalent squared epsilon squared divided by 2 C equivalent, which is 1/2 C equivalent epsilon squared. And you could plug in C equivalent as 2C, which is probably what I would do, except that the question literally says express it in terms of C equivalent, so there you go. All right, so hopefully that's a decent overview of circuits. You know, I expect circuits to be on midterm 2. They were not on midterm 1. Circuits are easy points, to be honest. It would be worth it to spend time now on circuits, to be good at them, and then, you know, move on to magnetism and so forth. So don't spend too much time, but don't be like, circuits are easy, screw it, I'm just going to do magnetism. If you spend time now on circuits, it'll pay off later when you come back and you want to review. And if you, you know, whatever work you do now is also going to be useful when we revisit with inductors later. So definitely spend some time on circuits just to get caught up. Next week we'll do magnetism, and that's an entirely new chapter. So for a little bit, we're not going to be looking at anything in terms of circuits or loop laws or anything. Some of that will show back up when we get to induction. So next week is magnetism. TBD if I cover magnetism in one session or two. I need to figure that out with the calendar because magnetism got a lot in it. And then after that is induction. So for a little bit, we're not going to be seeing anything like circuits or whatnot, and then it's going to make somewhat of a comeback in later weeks. But anyway, hopefully that clears things up. As always, thank you for watching. Appreciate it. And thanks for your questions. I always appreciate when you ask me questions. So feel free to reach out if you have questions about this, or if you want to discuss what to do next since if the midterm didn't go well, which I hope it did, but since it's that time of the year, if you want to plan moving forward to prep for midterm 2 and the final, feel free to reach out as well. I will see you next week. Have a good weekend. Take care.